Hi, my name is Benson, and I've decided to implement a behavior tree over a finite state machine for assignment 2. And to give a quick demo, my AI should act the exact same as before, but everything is running on a behavior tree. We'll shoot him a few times, and as you can see, it goes away. For this video, I'd like to highlight 2 design aspects that I've focused on. The first one would be the utility aspect, as implementing a behavior tree has really showed me how powerful something like this can be, especially when I compared it to a finite state machine. A behavior tree does not seem to exponentially expand the more actions and states you have. And this can not only be applied to AI, but to many things where a decision needs to be made in the future. The second aspect I'd like to focus on is the educational aspect. I've tried to structure this video and my code in a way where it'll show people kind of how to implement this and how all of the nodes and pieces of the puzzle come together. So I'd like to give a quick overview of my behavior tree and a quick run through. So our root starts with our selector. This selector is used to split between when the enemy can't see the player and when the enemy can see the player. And first the selector will run a sequence used to check if we can see a player. The sequence will run a check on can see player, which will invert the result. So assuming we can't see the player, this will return a false or a failure, which our inverter will turn to a success. And because it's a success, this sequence will continue on, and it will run our patrol sequence. A patrol sequence has 2 areas, the first being a selector, which checks if we have a path. And if we have a path, then good, continue on the sequence to move along the path. If we don't have a path, then generate a path, then return a success and move along that newly generated path. And what happens when we can see the player is our can see player will return a success. The inverter will then subsequently return it as a failure, which then will fail this sequence. And then the sequence will return a failure to the main selector, and the main selector will then go to the can see player side of the tree. And to run this, we have a sequence for checking if our enemy is healthy or not, whether to engage or to evade. So firstly, the sequence will run a selector, and the selector will run a check on is healthy with an inverter. If our enemy is healthy, the inverter will return a failure, thus allowing our selector to continue. Our selector will continue and run a sequence for engaging the player. The sequence will clear a path, clear the existing path of the enemy, generate a path to engage the player, attempt to fire at the player if visible, and then move along the engagement path. Assuming our enemy isn't healthy, is healthy will return a failure, which the inverter will return a success. And because the inverter has returned a success, our selector will succeed, which will continue our sequence. Our sequence will then start the evade player sequence. And the evade player sequence is the same thing as the engagement sequence, except the only difference is it will clear the path and then generate an evade path instead of an engagement path. And subsequently we'll try to fire at the player and then finally move along the path. So to go a bit into how to implement something like this, I have created an behavior tree manager that inherits from actor, and then we just chuck this into our world, and this will run all behavior trees that we declare and create. And our behavior tree pretty much just sets up all of our nodes, sets up our context, which is what the nodes require to run. It's all the data, sets up all the nodes, adds all the children and everything. And then in our tick, we then run the behavior tree where it will run through all of the children nodes inside our root node. And what our context is, it's pretty much all the data that the behavior tree requires. So in this case, since we're doing enemies, all we need is the enemy agents and the current enemy that the behavior tree is looping through. But obviously, if we had multiple different behavior trees, you can probably create a more abstract context and have other specific contexts inherit from it. So to begin, nodes construct every single thing inside our behavior trees. So I've created a node abstract class, which pretty much has a constructor that is used to set our pointer to the behavior context, which will then be accessed by all nodes, and evaluate function to evaluate the result of the node. So we have a node that inherits from our node class, and this is a composite node. A composite node is pretty much just a node that accepts multiple children. So the difference is we have an array of children nodes, and then we have a method to add nodes to that children node. And what this creates is a selector node, for example, which will run all children nodes until one is successful, and our sequence node, which will run all children until one fails or either everything succeeds. Another node type that inherits from our generic node is our decorator node. And what a decorator node is, it's a node that can only accept one child node, and then we also give it a method to set that child node. So for example, something that inherits from this node could be our inverter node. Our inverter node pretty much just says if we get a success, return failure, vice versa. And finally, the last node is our leaf node, which is arguably the most important node to be in the tree. Our leaf node is essentially a node that does an action, and this is what runs our AI. So it's pretty much the same thing, except we have a do action to do the action, and we override evaluate, so that inside the evaluate function we run the action and subsequently pass our result up the tree chain. So if we go to our actions, as you can see, all the bottom nodes are leaf nodes, has path, generate patrol path, etc. We have to declare these as actions, so I've created a action class, and essentially this file, all it does is it defines all the actions that our leaf node can do, such as can see player, has path, clear path, and in each one of them all we do is override our do action so that we can implement an actual action. And to show some of the implementations, for can see player, we check in our context for the current enemy that we're running the tree on if it can see the actor. If it can, then we can see the player, return success, otherwise return failure. And another example would be generate random path. We go into our context and our current enemy that we're looping through. We generate the path of that enemy and return a success. And this always returns a success because you pretty much can't fail to generate a path, at least in the context of our assignment. And to return finally to the behavior tree, with all these nodes, and pretty much we just declare every single node and set it up, so it's a bit of a mess, but pretty much an example would be we check if the player is visible, and if we can see the player, then if we can't see the player, then continue the sequence and go into the patrol path sequence. If we can see the player, we check if the player is healthy. If the player is healthy, then start the engage sequence, and if the player isn't healthy, start with the evade sequence. And then we finally add everything into our route and run the route.